In this video this afternoon, we shall be talking about Wronskian equations. Wronskian equation is a very powerful tool in linear differential equation, which is used to test for linear independence of a set of functions or a set of equations. It determines whether a set of functions or a set of equations is linearly independent. And what do we mean by a set of functions being linearly dependent and linearly independent? Let's write that. A set of functions, y1 of x, y2 of x, let's say till yn of x, is said to be linearly dependent. If there are constants, there are constants C, there are constants, let's say C1, C2 to Cn, such that not all of them, not all are zeros. Not all are zeros. That is, C1 y1 of x plus C2 y2 of x plus plus Cn yn of x is equals to 0. So in this case, not all these constants are zeros. And basically here, for Wronskian to be linearly dependent, it means that the Wronskian is 0. So if Wronskian, let's say, if Wronskian of y1, y2 to yn of x is equals to 0, that establishes the fact that the set of solution or the set of functions are linearly dependent. That is that about that definition. But for linearly independent solutions, a set of functions y1 of x, y2 of x, till yn of x is said to be linearly, let's just change this now, independent if there are constants C such that in that definition we will have constant C1, C2 and Cn such that C1 is equal to C2, so that C1 is equal to C2 is equal to Cn is equal to 0. So in this case, the Wronskian of the functions, let's say y1 of x, or let's say y1, y2 till yn of x, is not equal to 0. So if the Wronskian of a particular set of solution is not equal to 0, then we say that the set of function or set of solution is linearly independent. Okay, let's look at an example to buttress what we are talking about. Let's look at an example to buttress what we are talking about. But by and large, what is a Wronskian equation itself? How does a Wronskian look like? Before we go into examples, how does a Wronskian look like? Let's say for example, there are a set of functions that let's y1 of x, y2 of x till yn of x be set of functions, the n functions. Let them be n functions, each having at least n minus 1 continuous derivatives. N minus 1 continuous derivatives on an interval I. Okay, the Wronskian of these functions, the Wronskian of these functions is defined as Wronskian of y1, y2 till yn of x will be the determinants, okay, y1 of x, y2 of x, till when we get to yn of x, then y prime of x, y1 of y prime, and it's y1 prime, y2 prime of x, till when we get to yn prime of x. Okay, this is the determinant. Okay, yes. Then till when we get here to yn minus 1, y1 of n minus 1 derivative of x, you know, okay, yn minus 1 derivative of y2, y2 n minus 1 derivative of x, till when we get to yn minus 1 derivative of n of x. Okay, so it must not be equals to 0. Everything here must not be equals to 0. So if the value we obtain is not equals to 0, then we say that the Wronskian, you know, is the set of solutions, rather, the set of functions are linearly independent. So let's solve a problem and see what we are talking about here. Let's solve a problem. Let's solve a problem. Let's quickly solve a problem here. Let's give an example of how we use Wronskian. Let's give an example of how we use Wronskian. Okay? Let's quickly look at an example of how Wronskian could be used. All right. Now, we are given this equation. Given example, the differential equation y prime prime minus y is equals to 0. So find the general solution. That's it. Find the general solution. Find the general solution and determine whether the set of solutions is linearly independent. Okay, let's check that. Now, how do we solve this? Fine. First of all, we are given y prime prime minus y equals to 0. So we find the characteristic equation of this particular differential equation. You know, this is a second order differential equation. It's a second order linear homogeneous differential equation. Okay. Now let's take, for example, let's take a constant to represent where we have let's say r, you know, 2 should stand for y prime prime, r raised power 1 should stand for y prime, and r raised power 0 should stand for y. Sorry, r should be, yes, that should be r raised power 0 should stand for y. That's correct. Okay. Now, so in this case now, without substitution, we have y prime prime. The 2 is coming from the second degree here. The 1 is coming from the first degree here. This is second degree of y. That is the square y dx. This is the y dx, and this is what? Ordinary y. So here now we have r2, r raised power 2, minus what represents our y with respect to what? That is 1. Okay, because r raised power 0 is 1. You see that the exponent keeps reducing. This is just how we get our characteristic equation. So this will be what? This will equal 0. Okay, now r square now will be equals to 1. But by the time this one comes here, it becomes plus. So r will be equals to plus or minus square root 1. So r will be equals to plus or minus 1. So that means the value of our r here, we have two values of r. We have the first one is plus 1. The second one is what? Minus 1. Okay, so let's write that out before we get our general solution. So now say that what? R1 is equals to 1 and R2 is equals to minus 1. Okay, so in this case now, the general solution, since we have distinct and real values, the general solution is, since we have the y of x is equals to what? Is equals to C1 exponential R1x, you know, plus C2 exponential R2x. Okay, so that implies that y of x is equals to C1, that's this C1 and C2, you know, they are arbitrary what? Arbitrary constants. Now exponential, our R1 is 1, so x, because 1 times x is x there, plus C2 exponential, our R2 is minus 1, minus x. So this is the general solution. Okay, we have gotten the general solution for that problem. Now the next question is we have to find out whether the set of solutions are what. So here now we can say y1 is equals to exponential x and y2 is equals to exponential minus x, so that it forms the linear combination that we talked about the other time. Okay, now how do we now find the Wronskian? To find the Wronskian now, the Wronskian of y1 comma y2 of x, you don't forget, is the determinant of y1, y1 prime, and you can put of x if you like, okay, then y2 of x, then y2 prime of x. So let's find out that. So if you are able to get the value that is equals to 0, that means the set of solution exponential x and exponential minus x are linearly what? Dependent. And in that case, they can be what? One of the solutions can be written as a linear combination of the other. But otherwise, they will be what? Linearly independent. So we know that Wronskian now will be of y1, y2 of x will be y1 is what? Exponential x, while y2 we obtain is exponential minus x. So if we differentiate the y1 prime of x, if we differentiate exponential x, you still get what? Exponential x. If we differentiate exponential, that is for y2 prime of x, that is going to be what? That's it. Y2 is equals to exponential minus x. Can you still remember in differentiation? So the minus one will come, the minus will come here now. Y2 prime will be what? Minus exponential minus x. That's the differential value of exponential minus x. So you're right. Exponential minus x. Okay. So with this now, the next thing is to find the determinant. Let's find the determinant of this particular value. So that will be what? Don't forget determinant. The multiply this way, exponential x times exponential minus x. The minus. Don't forget this is minus will be here because yes, we obtain minus there. So minus will be here. Sorry. Then minus exponential x times exponential minus x. Okay. Yes. So this one will be minus exponential x minus x. According to law of indices, the powers be brought together. You add them together. The minus here is the one here. The minus exponential, you open up this one, x minus x. You're adding the powers together. Okay? So that will give us what? This will be what? Minus exponential, x minus x is 0. Minus exponential, x minus x is 0. So this will give us what? Minus 1 minus 1. So minus 1 minus 1 is what? 2. So, sorry, it's minus 2 rather. Sorry. It's minus 2. And since minus 2 is not equals to 0, that implies that we now conclude that the solution of this differential equation, what do you call it? Y prime minus y is equals to 0. That's the differential equation given to us, is linearly independent because the value of our Wronskian is not equals to 0. So on this, we have come to the end of this. But let me remind us, we could equally use Wronskian to find, or we could use Wronskian in the reduction method for solving differential equation. We could use it in variation parameters and the like. So these are other methods for solving second order differential equations. So don't forget to click on the notification bell, click the like, comment on my videos. If you have any questions you want to bring up, send it to the comment section of my video. I remain Dr. OJ. God bless you.